Okay, so picking up where we were last time, we were looking at this example right here. Remember the big ideas, we're computing vector line integrals. And sometimes you can take advantage of this theorem right here, a super convenient theorem in some cases, which says that, if you're interested in computing the line integral, but the curve in question is, I'm going to say, oriented an inconvenient way, right? There is no right or wrong particularly, but if it's oriented in an inconvenient way, what you can do is say, whatever, I'm just going to go ahead and orient it the convenient way, and I'm going to acknowledge that the opposite orientation that I want is simply going to result in an extra minus sign. Right? Super convenient way to answer a question. So, for example, you take we previously talked about going counterclockwise on the upper half of the unit circle, and we had a vector field given and blah, blah, blah. And we had to parameterize it and go through a whole calculation and compute an integral. Not that it worked out that bad, but still we had to actually do a computation. Here, what I pointed out at the very end of the last lecture is you can just say, hey, in this one we want to go the opposite direction. Oh, let me maximize this. We can fit it all on. You want to go the opposite direction? Okay, the opposite direction simply amounts to this extra minus sign, and we've already computed that integral going in the convenient direction as being pi, and so therefore our answer is, don't forget to carry the minus sign, minus pi. Right? Super convenient. Awesome way to solve the problem. Now that said, you won't always get that lucky. You won't always have already done it the other way. So I do think it's a good exercise to think through also, how would we do this sort of, brute force? How would we directly compute this? And punchline, we're going to have to parameterize the curve. Keep in mind our curve here is clockwise. Right? So I want to parameterize like this. How are we going to parameterize like that? I'm going to show you two different ways to do this parameterization. Again, tools for your toolbox, right? You never know which tool is going to be useful in what circumstance. So, first point of view, which I like, and this is useful in a lot of different contexts, document your parameter right there in your diagram. So here, I'm going to say, look, if we're going clockwise like this, that means that at time equals 0, I'm there, and at time equals pi, I'm there. And so that angle then, that's fine. That angle, what I've labeled t, this is the thing that is 0 when I'm at the point that I'm starting at, and that increases through and becomes pi at the point that I'm ending at. Yeah?
Instead of that, if we interpret it as like the normal cos of t, sine of t, but going from negative pi to 0, does that?
I'm going to talk about that in a minute.
Okay, right.
Yeah. So I'll totally answer that question, but yeah, just let me work up to it. Okay, so once you document what your parameter is, then you can say, all right, well, then this angle becomes pi minus t. And by the way, that angle is what I'm going to call our usual polar angle. That's what you might call theta. And we have a pretty convenient formula to describe position if you know the polar angle theta. And the answer is that it's cosine theta sine theta, right? So you just take this formula for theta and put it right there, and polar coordinates gives you a parameterization. Yes, by the way, you do have to know either the angle addition formulas or all of the appropriate symmetry properties of sine and cosine to be able to rewrite that in the nice simplified way like this. So do make sure you know all those symmetries. Do make sure you know the angle addition formulas, all necessary for this course. Okay. Now, here's a different way to do it. We're going to get the same parameterization. Not that we have to, by the way. A different parameterization would still be cool, but this different method's going to give us literally the exact same parameterization. Another really neat observation. What I want, this parameterization, x comma y, that I'd like to be able to compute. Sometimes you get lucky. And in this case, we notice it is literally a reflection over the y-axis of this parameterization that I already know is cosine t sine t. Sweet. Right, you get lucky sometimes. And in fact, it's really easy to see how this reflection works even. The way you reflect over the y-axis is by inserting a minus sign onto the first coordinate. It's right here in the geometry, right? Y-coordinate doesn't change. The x-coordinate gets a minus sign. So, boom, same answer. Now, again, different tools for your toolbox. There are, the point to these examples is not to prepare you for how to solve this exact question. It's to prepare you for other questions, who knows what, that might come up. So just try to, think about this from the point of view of the broad stroke and the big picture, the idea of representing the parameter on your diagram and then seeing what you can conclude from that and, follow your nose to try to get to where you need to get, depending on the specifics of the situation. And then likewise, look for reflections. Just keep an open mind about the thing that you want might be easier understood in relation to something else that can be related by way of a reflection. Anyway. Okay, so to your question in the back, that's what I'm going to call the fourth method that could be used, I suppose, to solve this problem. And that would be to say, look, we're going to, we're going to use this same parameterization that we did previously. We wrote this down. Now, of course, that goes counterclockwise. Let's not go in the direction we're supposed to now. Our new example, we're interested in clockwise. But if we use the same parameterization, why couldn't we just write down integral from pi to 0? Blah, 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 all the same stuff. Now, this is very tempting. I have a bit of a problem with this. And because if you think about it, this thing that we're having go from pi to 0, keep in mind that's our parameter t. Keep in mind furthermore, t is what we think of as being time. So we're having time start at the larger value and end at the lesser value. I feel like time's going backwards here. I feel like that's a science fiction movie. I don't really know how time travel works. I don't really want my mathematical arguments to be contingent on your believing my claims about time travel. You see what I'm saying? So that as an argument, I think it's really fishy. Here's another little nasty point. You say, one could say, okay, well, yeah, but look, this just says we're going the other direction. But are you? Because check this out. You're using the same parameterization. It has the same derivative. That seems to suggest that your parameterization's not going the other direction. I think there's some sticky points in here, right? And that making a really crisp and clear and unambiguous is important, right? It has to be perfectly clear what the point is that you're making. I think there's a lot of sticky ambiguities in what is the claim being made here that I think make this not a very good argument. So now, for your consideration, I'll point out one other thing. Yes, it does give you arithmetically. Why am I erasing that? I wanted to keep that. You will get numerically the correct answer. But if you think about it, the way that I can persuade you that you will get the numerically correct answer, by far the easiest way to do that is just to recognize that when you switch your bounds, you're just introducing a minus sign from the formula from the fundamental theorem of calculus, and introducing a minus sign is this argument. So just make this argument. No time travel, right? No funny business. No ambiguity as to what we mean. We're citing a theorem that's right there. This is much more crisp, much more clear of an argument. And again, I remind you, it's not about the answer, it's about the argument, right? And this is a much more clear argument. Everybody on board? Does that answer your question?
Yeah, but I have like one more question.
Okay.
Stemming from that. What
Yeah.
it was like, instead of going from pi to 0, you went from negative pi to 0. Or then does that mean you're...
Well, then you're not even going along the correct path, right? So if you take this, if you take this path, but from negative pi to 0, negative pi to 0 would have you doing this. That's not even the correct curve.
Oh, okay.
Yeah. Right. I honestly, I think it's going to be hard to make a case for why you need something better than this. Right? That's pretty streamlined. Right?
I was just thinking.
Yeah. No. Yeah. Sure. I think it's going to be hard to beat this. Yeah. Okay. Good. Okay. So on to the next thing. This is a physical interpretation point, and really useful idea that we're about to develop. And it's going to come from trying to reinterpret what is a vector line integral. And now let me remind you, we already know that vector line integrals represent work. But that was with the assumption that the integrand is representing a force. Right? So that was our premise. That was what we started with. Hey, we've got a vector field that represents forces. And how would I compute work? And it turns out that this is the construction that does it. Okay, fine. Here's the thing. That is one of our two primary interpretations of vector fields. Vector fields very often are used to represent forces. So it's nice to know what vector line integrals represent in that case, but what if, very reasonable question, what if our vector field does not represent force? What if our vector field represents the velocity of a fluid flow? There's no force involved here, right? Maybe our fluid is like air, right? And it just doesn't really push with a significant amount of force, right? So if that's what this is, now we have a totally new question, which is, okay, now what does that represent? What is a vector line integral when the integrand is a fluid flow instead of a force? And we don't have an answer to that question yet. Okay. I'm going to show you a computation that will kind of resolve this. There's a lot going on in that calculation. I like having a convenient reference, and I had a little space at the bottom of this page when I was writing these notes, not enough to actually start with the next big thing, but I figured it'd be convenient to have this little diagram and summary of relationships that is nice to be able to make use of here and there. So I just copy pasted this from earlier. And before I start off on the answer, let me give you a little bit of context. There is going to be something very disappointing about the answer. The answer is not going to be something that we have a word for already. So this is going to seem like it's going to seem unconclusive, right? There is something really nice about, okay, hey, what does this expression represent? Oh, argument. Oh, it represents work. Boom, done. Satisfying because we have a name for it. And we have previous experience with it, right? I'm sad to report that this, when the vector field represents a fluid flow, this is not something that we probably have any previous experience with. And it doesn't really have a name particularly, at least not in general. So the answer is going to be that it's sort of this represents the answer to another question, as it turns out. So anyway, I prepare you in advance for the disappointment, perhaps, that's about to follow, and it's sort of natural in the circumstance. So anyway, here's the question I want to ask. Suppose we have a curve, and suppose I have a fluid flowing along in some way, something like that. And suppose I take some area, A, and I kind of drag that area along the curve and therefore define a thin little region R, kind of like this. It's all like a little. It's almost like a tube, except it's not enclosed. It's not really a tube, but a real thin little region, kind of a neighborhood, vicinity, you might say, of the curve. So I want to talk about this fluid, just the fluid that's, again, appropriately close to that curve. And what I want to ask about that fluid is, altogether, to what combined extent is it flowing along the curve? I know that sounds like a weird thing to ask, right? But ultimately a pretty reasonable question, because if you look at each little piece of fluid, right, if I were to take some little piece of this fluid, something like that, I can talk about how much fluid that is in that little piece. And if the velocity, as given by the vector field, is this, I can also talk about the extent to which it's flowing along the curve. And I can just straight up write that down. Here's the extent to which it flows along the curve. It's a component, which is a dot product with the unit vector. Don't forget the unit vector, of course, is our capital T. That's the unit vector pointing in the direction of the curve. So there's that component, and how much fluid is it? Well, that amount of fluid is area times ds, ds being kind of the thickness. So it's a matter of writing it down. Right? Now, that's just for this little bit of fluid. We are interested, of course, in all together, all of the fluid added up over all of these pieces. And let's see here. Oh, gosh, let me do it like this. So, whoops, colors. Adding up over all the pieces, over the entire curve, you get an integral, and you can kind of move terms around. And one thing that's kind of nice is to rewrite it in this form right here, and notice figuring very prominently in that answer is a vector line integral. So right off the bat, what we see is that we're flirting with a pretty good answer to the question, which is this vector line integral. We're going to figure out what the deal is with that area, but this vector line integral is a large part of the answer to this question. And so, said differently, I can kind of say that this question is really more of an answer. This is kind of, sort of, we've got to figure out what to do with that area, but this is kind of, sort of the answer to how do I interpret a vector line integral. It's a commentary on how much the fluid is flowing along the curve. All right, now, yes, I do have to address that matter of the area. What's the deal with that area? Don't forget the area here. It tells me how big the cross-section is. I'm going to say that the fact that there's a factor of A here is unsurprising. After all, the bigger the area, the bigger the region. The bigger the region, the more fluid. The more fluid there is, the more fluid there is to flow along the curve. So the fact that our answer is proportional to area, again, I'm going to say unsurprising, right? So since that's ultimately not really what I'm interested in, I'm interested in the line integral. I'm interested in the computation being done on the curve, not how sort of much vicinity around the curve. I'm going to say, look, we're going to interpret our answer as that the vector line integral, wrong color, the vector line integral is how much fluid's flowing along the curve per unit area of cross-section. So effectively, we just kind of want to get rid of that area. And by the way, the only reason I included the area in the first place, I mean, why include area in the calculation when you just want to get rid of it moments later? And the answer is because I needed to be able to talk about actual quantity of fluid. And you can't talk about quantity of fluid unless there's some actual volume in which that fluid can be, right? So I have to introduce area get our sort of hands on the idea of fluid, and then I recognize that, well, yeah, but that's not really what I care about. Okay, yeah?
Yeah, so like in essence what you're trying to say is that the line integral isn't just for work. It can be used for
Yeah.
work.
Oh, yeah, absolutely.
Okay.
Absolutely. And for whatever it's worth, that's the same with every other kind of integral we've talked about, right? And we motivate some integrals by, interest in, volume or mass or work or population or whatever. And, we start with one interpretation and then we sort of observe that, you can interpret it in different ways. So same thing here. We have a new interpretation now of vector line integral in this context of fluids.
And you said that it's per cross-sectional area. Why
Mhm.
is it like the line?
Oh, yeah, so think of it this way. I could take this factor of area and kind of make it a denominator over here
Yeah.
and say the answer to this question, that the answer to the question, if I were to divide by the cross-sectional area that I didn't really care about in the first place, then what you end up with is an interpretation of the line integral.
Okay.
Yeah, yeah. All right. Okay, so let's see some examples here, just to get our kind of hands on it. And I'm going to do the examples in the context of a special case where our domain curve is a closed curve, which means it starts and ends at the same point. Now, this is a very important special case. It's going to turn out to be of surprising importance and a bunch of stuff we're going to do as we go throughout the class. But ultimately, what we're talking about here is still just the vector line integral. It's just a special case of the vector line integral where your curve kind of ties itself off at the end, right? It ends up at the same point that it started at, and so it makes a loop, sort of. Okay. And in that special case, by the way, the term we use is circulation. Lowercase Greek letter sigma, very often. Okay, so let's draw some pictures, and we'll start off by thinking about let's see here, vector field, colors, vector field F. So we've got a vector field like that, right? And let's see here, let's think about the dx vectors. Well, dx vectors, of course, these are little tangent vectors representing displacements along the curve as we go around the curve. And now let's look at these dot products, f dot dx. Just look at these little vectors. Look at the green dot blue on each of those pieces. And, well, those vectors are going in the same direction. The dot product's going to be positive and significant because they're really pointing very much in the same direction. Right? That's not like we have some orthogonality or something there. So you would expect this circulation to be positive. Does that make sense to everybody? Now let me take a different angle on this, a little bit of a different angle. We've already agreed that vector line integral represents the extent to which the fluid flows along the curve. Okay, well, wait a minute. The curve is going around in a kind of a sort of a circle. It's a closed curve, so it's got to kind of come back around. Now, is it exactly a circle? Not really the point. If it's a closed curve, I'm going to make a geometric appeal here. If you keep track of the tangent vector, the unit tangent vector, that unit tangent vector has to make exactly a loop, right? The unit tangent vector goes around literally in exactly a circle. So the points that the curve travels might not be a circle, but the tangent vectors will go around in a circle. Okay, so let's see here. Let's connect the dots again. The line integral represents how the fluid is going around the curve. The curve is going around in a circle. You kind of connect those two together. And a reasonable interpretation is that the line integral represents the extent to which the fluid is representing a flow that's kind of going around in little circles in some sense. Yes?
How does this relate to like curl, if at all?
Yeah, no, it does massively, and it turns out a really big question, and that's going to be several days of lecture. Some of it's going to be on Friday, and some of it's going to be within a couple of weeks. But yeah, there's a lot to say about that. But yes, there's a very strong connection, and that's a good observation. Yeah. But yeah, I'm going to have to blow that off for a later time. Yeah, yes.
Sorry, could you repeat why we have a positive circulation with this?
Well, yeah. So if you look at you got the vector field and the dx, right? So the vector field is like this, and the dx is like that, and they're pointing in the same direction. And a dot product of two vectors that are always pointing in the same direction is positive. So we're adding up a bunch of positive terms here.
Yeah. So
Yeah.
the dx is the kind of the loop that's formed.
The dx's are literal displacements along the curve.
Okay.
Yeah. Yeah.
Thank you.
Okay, so line integral represents the extent to which the fluid is following the curve. The curve has directions going around in circles. The line integral kind of represents the extent to which the fluid is also it has directions going around in circles in some sense. It's representing kind of a rotation of the fluid. This is loosely speaking, of course. So that is a really nice interpretation, and related to this interpretation down here, if you were to imagine this being a little small object, like a leaf that fell into the surface of a river, something like that. Right? And if you think of, okay, well, this circulation here represents the extent to which the fluid is there's a rotational aspect to the fluid. Well, that also suggests the extent to which the fluid would literally rotate the leaf that's floating in that fluid. So it represents kind of a rotation a resulting rotation of objects in the fluid. Now, what I do want you to notice, a distinction here, we talked about this back in Chapter 3. This is not to be confused with flow lines. Now, here's an actual flow line for this vector field. Notice I didn't say flow line anywhere along the line. Right? Coincidentally, in this case, yes, the flow line also kind of goes around, and it's a common misconception for students to think that circulation is a statement about flow lines. It 100% is not. It's just not. And so I'll remind you, back in Chapter 3, there's an example where we saw, let's see, the if I remember correctly, the flow lines of that example were all straight lines. No curvature of the flow lines at all. And yet there was still a rotation in the fluid because of how the fluid kind of going in different directions at different places, it still creates a rotation. Okay, so please don't make the mistake of thinking that flow lines have anything to do with this. Okay, yeah.
So with the vector field where the vectors are all, like, let's say going like one direction,
Yeah.
and you still have a closed curve,
Yeah.
Is that closer to like, is it work? Or is it circulation?
Work means force dot displacement, and there's no forces in discussion. I mean, you could create forces by saying, assuming that your fluid has a certain amount of, mass to it, and that it's got a certain amount of, friction or something. But there's a lot of physics that you have to kind of make up and incorporate into the problem to make any such connection there. So yeah, very importantly, you should not try to connect this to work. We're just making a different sort of take on it. Yeah. Right. Okay. Last point I want to make, and then we'll move on to the next thing. You will notice that the field arrows that I have drawn there and the field arrows that I have drawn here are the same. In fact, I think I literally did a copy-paste on those. I think they're literally exactly the same arrows. There is a temptation to say that the circulation here and the circulation here, well, of course they're the same. It's the same fluid. You see the temptation, right? See the allure there? That's not true. Very importantly, circulation involves not just the vector field. Circulation also involves the curve. It involves which direction are you going along the curve, right? And the curve here is counterclockwise. The curve here, you'll notice, is clockwise. So I think a nice way to think about this, sort of the distinction between these two examples, and what you might call these two questions. The question on the left, by virtue of the curve going counterclockwise, think of circulation here on the left as asking, to what extent is this fluid flowing counterclockwise? Because the curve we're comparing the fluid to is counterclockwise. Think of this circulation as asking a similar question, which is, to what extent is this exact same vector field rotating clockwise? Because the curve we're comparing it to here is clockwise. So, yes, it's the same fluid, but we're asking two different questions about it. We're asking kind of exact opposite questions. To whatever extent it's counterclockwise, well, it's negative of that amount clockwise, because those are opposites of each other. And so the circulation here, naturally positive, but the circulation here, negative, because we asked the opposite question. Okay, so let's see here. Last little quick comment. Both of these examples are drawn for sort of maximum convenience. Curves are easy when they're circles, and fluid flows going literally exactly along the curve just to make the geometry kind of convenient and nice starter examples. Don't assume that it'll always be exactly that convenient. Sometimes, for example, here, it's just not that convenient. And you'll notice here, for example, as the curve is going in that direction, the fluid is going the opposite way, whereas on this part of the curve is going that way, and the fluid is also going that way. So when we're looking at these contributions to the circulation, some are negative, some are positive. And when you add that up, just looking at the geometry, I don't think it's exactly clear who's going to win that tug of war between negative and positive. So in this case, you'd really just have to crank out the integral, algebraically, I'll say. Yep.
If the vector field has no curl, can you assume the circulation is zero?
Assume is not the right word there. There is so this relates to his question. There is a very strong connection between circulation and curl, and I want to leave that to be a punchline, and that'll become later, probably on Friday.
Right.
Yeah. It's a great question, but I'm gonna. There's a lot to say there. Yeah. Okay, so keep your eyes out for freebies. As y'all know, I like shortcuts, right? I've benefited from shortcuts massively when I was in college. I hope y'all will too. I showed y'all already my favorite of the various little shortcut tools that I've used. And here's another one. This is a respectable second place. I don't think it's quite as useful as symmetry arguments, but this comes up quite a bit as well. And so be on the lookout for this kind of thing. Let's start by recognizing what a brutally difficult question this would be if I were to do this by, directly. I've given you a curve that I describe here in spherical coordinates, which means if you wanted to write this in rectangular coordinates, as would be necessary for algebraically computing this, in order to be able to do the dot product, for example, you need it in rectangular coordinates. You're going to have rho sine phi cosine theta, then rho sine phi sine theta. You're going to have these horrendous, just terrifying formulas for x, y, and z. So this curve is a nightmare. Everybody believe it? Okay. Let's look at the vector field here. Not so bad, I suppose, but still a little weird. X squared times y is going to be pretty horrendous on its own because, again, x, y, and z are horrendous from that, right? So nightmare of a computation we're looking at here, if you do this the old-fashioned way. So, okay, here's the clever convenience, and that is to think about geometry. We're going to start off by noticing that our curve, among other things that I know that I don't need to refer to, I know that every point on this curve is on the unit sphere, because rho is equal to 1. Next, geometric observation on any surface, sphere, plane, whatever, doesn't matter, any surface, if you are moving on the surface, then your direction is parallel to the surface. Geometric appeal, right? If you're on imagine the desk surface here. If there's an ant walking around on the surface of the desk, his velocity is always parallel to the surface of the desk. Is that believable? Okay. All right. So our dx vector, just because of this geometric argument, I know already that my dx vector, this thing right there, is parallel to the sphere. All right, now let's think about our field. Our field vector there, and you're going to notice that there is a scalar. I shouldn't use gray. Let's see here. I'll use orange. There we go. I have a scalar, x squared y. Keep in mind, scalar means just a number. It does not mean constant. A lot of people misunderstand and say constant when they mean scalar and vice versa. But this is a scalar, non-constant scalar, multiplied by position vector. And this is another little bit of geometry. Position vectors of spheres. This is a unique symmetry, you might say, of spheres. The position vector is a radius, and radii of spheres are always perpendicular to the sphere. Right? If you on the surface of the Earth, right, on a nice flat spot on the surface of the Earth, if you dig down, namely towards the center, you are also digging perpendicular to the surface. Right? Well, if x is always perpendicular to the sphere, then that means that the field vector is also perpendicular to the sphere. Okay, now, so we've made a couple of geometric observations here, and there's a really nice punchline from it, and that is, let's see here, keep in mind what I'm computing in the first place. I'm adding up a bunch of f dot dx. Well, f dot dx, one of them's perpendicular to the sphere, the other one's parallel to the sphere. That means they're perpendicular to each other. That means all those individual dot products are zeros. That means in this integral, I'm adding up a bunch of zeros, and that adds up to 0, and we're done. No nasty trig, right? No horrendous integrals. Just capitalizing on fortunate geometry. Ever see how that worked? Now, you may be thinking to yourself, okay, this is a highly manufactured example. When in the real world will you get that lucky? I'm going to say quite often. That was my experience anyway. And I bet you're going to have a similar opportunity. I would say somewhere in the range of about 10% of the integrals that I saw as a undergrad physics major. So keep in mind, 20%, 0 by odd symmetry. Another 10%, 0 by convenient geometry. We're up to almost a third of my physics major, right? Poof, disappears by clever arguments. Really nice. Okay, please be on the lookout for all this kind of stuff. Again, not that manufactured. This kind of thing happens a pretty fair amount. Okay. Next. This is just a bit of notation. I don't want to get too wrapped up in this because it's just notation. But known formula from chapter 3. X prime we know how to write out in coordinates. distribute the dt. I didn't really do anything substantial there, right? I'm just kind of writing stuff down. And then pretty reasonable that, for example, z prime dt, shouldn't we call that dz? And likewise, these, shouldn't I call those dx and dy? All together then, we have a pretty reasonable coordinate expansion, you might call it, of our position differential, our dx vector. Okay. Who cares? Well, dx written in coordinates like so. The vector field that you are doing a vector line integral of for whatever reason, fluids or forces, who cares, whatever, any vector line integral you might be looking at, that vector field has coordinates that you can write down. And then you can just take this dot product and dot it on out like so. And altogether, what we get is an alternative notation for vector line integrals. You can rewrite this, sort of general, this is kind of my favorite notation, for vector line integrals f dot dx. Instead, you can write it as integral p dx plus q dy plus r dz. Now, why would you ever want to do that? Right? It's bulkier. Right? That doesn't look very convenient. Why would I want to write it? It goes halfway across the page. That's not convenient. Unnatural in a way. I mean, let's take a moment to appreciate this notation on the left. F is the force, or if we're talking about fluids, it's the velocity. It's something physically natural. The dx is a displacement along the curve. It's geometrically natural. That what I write down here, I can see where it comes from right in my original question. What in the world, I ask rhetorically, what in the world is q dy? And the answer is it's not particularly natural. It's not something that you can look at in the question and say, oh yeah, there it is. That's what q dy represents, that thing. Not really. So I think I've made a pretty convincing argument against this notation that I just showed you. That brings up the question, why would I waste your time with it? And there's two reasons. One's cultural, one's practical. The cultural note. This notation is pretty much how you write down integrals of differential forms. Differential forms are a very sophisticated, modern, as in, less than 100 years ago. Very sophisticated, very modern point of view on these kinds of things, and it's extremely powerful. Differential forms are how you prove some really big theorems about. In fact, even some of the stuff that we're going to do in this class, I am not going to prove. Too sophisticated, can't do it in this course. It uses differential forms. And again, not really what this course is about. So anyway, that is, very legitimately a great reason to want to use that notation. It just doesn't come up in this course. Okay, so the second reason that I have to show you this notation is practical, and the punchline is, this notation is in common use. You are going to see this notation, whether I like it or not, right? It's out there. It's in future engineering textbooks, for example. So you're going to have to know what to do with this when you see it. Right? Now, why do they use this notation? Why don't they just write it like this? It'd be much more easy to understand if they write it like this. Well, they like to use this notation, again, because they understand that differential forms are very powerful, and there are, therefore, really good reasons to want to write it like that. So, what y'all are going to do, what I encourage anyway for y'all to do, is when you see an integral written like this, think to yourself as follows. Think to yourself, okay, the dx, dy, dz, this is really just kind of an expanded expression for the dx vector. And the p, q, and r, this is just the coordinates of the vector field, and with that sort of inferred, with the P, Q, and R inferred as the vector field F, you can reinterpret that weird-looking notation as that vector line integral. All right, so you can just kind of reverse this process that we went to here and interpret something like this as something like that, and specifically you can see exactly what the vector field is that you're computing a line integral of. Okay, all right, so that's really all you need to know. Okay, let's see here. Probably the last thing we'll do today. We'll see. I'm going to start off with a bit of good news. We have another symmetry theorem. Reminder, symmetry theorems are awesome. Symmetry theorems are computationally super convenient, saves you loads of times. We've seen the single variable odd symmetry theorem, double integral odd symmetry theorem, triple integral odd symmetry theorem. And now we have the scalar line integral odd symmetry theorem. And you're going to notice from the way this is written down, it looks like it's a shameless ripoff of all of those previous theorems. And at 100%, yep, totally, it's morally the exact same idea. It's true for basically the same reasons. You use it in basically the same way. You get basically the same warnings. Yeah, you got to check and make sure both conditions hold. Yeah, you got to make sure that the symmetries are through the same line. It's the same applied to a different setting of scalar line integrals. So have fun, use it. It's a good theorem, big fan. Downside, warning, this is unfortunately just for scalar line integrals. Very importantly, only scalar line integrals. If you try to use this for vector line integrals, it doesn't work. There is no such theorem. If you were to try to create such a theorem, you would fail. It doesn't work. It doesn't fit. It's just not true. Right? And I always make a big deal out of this because, again, it's one of these things where the bigger a deal I make, the less students step on that landmine, and I don't want anybody to step on the landmine. If you want to know roughly why the theorem fails, if you would imagine a symmetric curve there, symmetric over a line about like that, right? That reasonably, give me some artistic flexibility there. It looks like a symmetric curve. Over that line. Keep in mind, line integrals can be written, for example, like that. Part of the line integral, then, is the unit tangent vector. And when you look at corresponding little chunks, like if I were to look at this little chunk of size ds and that little chunk of size ds, the unit tangent vectors at these two pieces, terms in the Riemann sum, you would hope would cancel. But look at these tangent vectors. They're not the same. The ds's are the same. The tangent vectors are not the same. They're also not negatives of each other. They're not anything particularly convenient to an odd symmetry theorem. And it just straight up flat does not work. There is not a cancellation. So we lose. So, sorry to be the bearer of bad news. Anyway, again, extra important, make sure you don't try to use odd symmetry for vector line integrals. It does not work. Okay, let's see here. We have very little time left. We have 1 minute. Let me make a super quick comment and then we'll wrap it up. We are done with 6.1. We're going to start with 6.2. The first couple of pages of what I have here for 6.2 is actually kind of a run-up to all of chapters 6 and 7. There's a common underlying shared idea in a bunch of the theorems that we're going to talk about. And so the first couple of pages here are going to be some seemingly general abstract stuff that you might not see why we would care about as we're doing it. Just please be patient with me when we get to this. It will all be really important very soon. Okay, we'll call it a day right there. See y'all later. Have a good rest of your Wednesday. Don't forget about attendance. Whoops.